All right, so I'm going to show you how to construct a slope field. And then the slope field is going to tell us something about the function. All right, so let's take the derivative function. All right, so let's pretend we have the derivative. And the derivative is equal to x. All right, so I'm going to make a table to construct a slope field. So let me pull some values. I'm going to go from like -3, -2, -1, 0, 1, 2, 3. Okay, those are my x's. My y, I don't know what my y value is going to be because I don't have the function. I'm not sure, but I know what my derivative is going to be. Because if I put in -3 into the derivative function, if I put -3 in here, I just have y prime is equal to -3. If I plug in -2 here, I just have y prime is equal to -2. If I plug in -1 here, I have y prime equals -1. If I plug in 0 here, I have y prime equals 0. If I plug in 1, I have y prime equals 1. If I plug in 2, I have y prime equals 2, and so on. So I just get the exact values, the same values. All right, so how a slope field looks is, since I do not know what the function itself is, I don't know what the y value is that I'm talking about. All I know is, let me start with 0. At x equals 0, at all x equals 0, for all y values, the slope has to be 0. So a slope of 0 looks like a horizontal line. So for any y value, as long as x is 0, the slope has to be a horizontal line. So at all these guys, I have a horizontal line. All right, now I'm not going in order here because I want you to see specific ones. I'll fill them in all in a second. At x equals 1, my slope is 1. So here's x equals 1. So for every single y value, if x is 1, slope has to be 1. So that means that at this slope of 1, it sort of looks like this. Slope of 1, 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 slope of 1. That's true for all of those y values. All right. If I look at x equals 2, x equals 2 right here, my slope is 2. So that just means I'm going to be a little steeper. So I just have to sort of make this line look a little bit steeper than my other line did. And these are all representing the slopes. Okay, and this is going to seem super weird, but I'm going to show you the other side, which should help you a little bit more. All right. Now, if I look at x equals -1, which is right over here, x equals -1, the slope should be a -1 slope. So -1 looks like this. Downward, 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 downward. So you're almost sketching a tiny little piece of the slope of a line or the slope on a line. All right, so then if I go now to -2, my slope is -2. So I'm going to have at -2, which is here, a steeper negative line. So it will look more like this. And if I kept going, if I went out to -3, my slope is -3. So it'd be even more steep than the one before. And if I just keep filling in all these guys, if I went to 3, the slope is +3. I'm constructing myself a slope field. And the slope field is going to allow me to figure out what the function y has to look like. Because if I look at the slope field, I notice that it forms this parabolic pattern. So I know that my function has to be some type of parabola if I want it to fit into this slope field. All right, so now check what happens if I integrate this. Okay, so to integrate this, I know that I'm going to, because I want to find out the function itself. So I want to go backwards because I have the derivative. So to integrate this, I'm going to integrate, whoops, I have a little spot. x with respect to x, or x dx. All right, so I'm not finding the definite integral. Notice it's an indefinite integral. So when I take the integral here, I add 1 to the exponent, I divide by it, and then I know I have to add a constant. Remember this difference here. We did this a few weeks back. When the numbers aren't here, you're finding definite integrals. When the numbers aren't there, you're finding indefinite integrals, so you have to add that plus c. So that means that my function f of x is x squared over 2, or I'm just going to rewrite it. I'm going to write it as 1/2 x squared plus c, which is exactly a function that's a parabola that c pushes up or down, and that's why this slope field makes sense, because any parabola that would fit in the slope field, the value of c can change, but they all would satisfy the slope field. So if my value of c was 1, 2, 3, 4, then the black one that I drew was perfect. If my value of c was -2, then the parabola passing through -2. All right, let's check out another one. So let's pretend that our derivative is x squared. So let's make a slope field for this. All right, so I'll make a table of values. I'll go from -3 to +3. These are my x values. I don't know my y values, but I do know my derivative values. Because if I put in -3 in here, I have -3 squared, which is 9. If I plug in -2 here, -2 squared is 4. If I plug in -1, -1 squared is 1. 0 squared is 0. 1 squared is 1. 2 squared is 4. 3 squared is 9. Okay, so now I can construct a slope field here with all those values. All right. So at 0, I just started 0 just because it's easier to start with the origin. So at 0 here, my slope is 0. So that means 0 slope is a horizontal line. So that means I have horizontal lines at every single y value that has an x value of 0. All right, moving on. At 1, I have a slope of 1. So at 1, I have a slope of 1. So 1, 1. This is just an estimate of what a slope of 1 would look like. Because really the most important thing is to see what happens next. So to see at 2, the slope is 4, which means it's steeper than that. So I'm going to make it steeper. Slope of 4 would be steeper. Okay, and then at 3, the slope is 9, so that would be even more steep than that. So I don't want to make it look like a vertical line, but I do want to just make it look a little more steep. These are kind of fun. All right, now at -1, the slope is 1. So check this out. At -1, the slope is 1. So slope of 1 looks like this. This is different from before because we had the shape turn around at some point. And then at -2, it's 4. So that means it's more steep. Trying to make it look more steep. It's definitely not negative, so that's important. And then at -3, it's 9, so even more steep. So my slope field tells me that my function has to fit inside here, which looks like this. Flattening out and then coming back around. All right, so now let's integrate and see what the actual function is. Okay, so to find f, I add 1 to the exponent, divide by it, plus c. This is a cubic function, and cubic functions have this shape. C value could change, so 1, 2, 3, 4, 5, 6, 7. If the c value was 7, it would be up there. And say if the c value was -2, the function would be something like this.